All right, mic check. Welcome back to CS196, everyone. So today is Tuesday, a wonderful Tuesday. I need a haircut, and today we're going to learn about smart pointers. So let's go over the objectives for today. So like I said, we're going to be covering smart pointers, what they are, applications of smart pointers in Rust, and then we're going to go ahead and talk about linked lists, which is a form of smart pointer applications in Rust, and we'll talk a little bit about it. But assuming that you guys have touched on it in CS125. And we're also going to talk about doubly linked lists, which is another form of linked lists, and will allow us to introduce some new smart pointers. Essentially, it'll be the driving topic of our smart pointer lecture today. So let's go ahead and go back to a little bit of a review that we talked about in a previous lecture. We talked about how computers use memory. It's quite obvious, of course. Nobody should be surprised about this, but we talked about how this memory can be represented as these blocks that are addressed at these hexadecimal numbers. And so, really, this is kind of all you need to know about memory, that it exists and that they're formed as blocks. And so when we talk about linked lists, I think it's helpful to look at how other data structures are represented in memory to understand, the significant differences between a linked list and something like an array, for example. So let's talk about an array. So what does an array look like in memory? Well, it is quite literally just a block of memory. We call it a contiguous block of memory. And this word contiguous, all it really means is that these blocks of memory are touching each other. And so because of this property of arrays, we can address them, or index them rather, starting at 0, 1, 2, whatever you want to call it. And so since they're so close to each other in memory, we can actually reference them by indices. So 0, 1, 2, 3, 4, 5, 6 in this example. So what about linked lists? Well, linked lists are a bit different. We can't use indices to reference blocks in linked lists, and that's because of the way that they're kind of laid out in memory. So if we look here, one linked list node, we have it just kind of floating out in memory here, addressed at this address. And so let's introduce another node here. This is kind of another just sort of block of memory somewhere out there. Let's introduce another node. So here's another one, just kind of floating out in memory. We have no idea where it is. It's just, not really close to this other node or this other node, similar to what we saw with the array, etc. You guys get the point. So in order to kind of link these together, we need to use pointers. So, this node will point to this node, and this node will point to this node, and so on and so forth. So in memory, compared to what we saw with arrays, linked lists are quite scattered around. There's no guarantee in where it will be, where specific blocks of memory will be for each node. So that's a little bit of a review of linked lists, where I'm assuming that you guys have covered them a little bit in CS125, so I don't want to talk too much about it. Today's focus is going to be about Rust and smart pointers. So what do linked lists look like in Java? Well, this might be a little bit different than what you saw in CS125, but very similar. It's just kind of like an object where each node has some data and a pointer to the next node. The only thing that you might not really be familiar with is this little, greater than or and equal to and less than equal to signs. Don't get too terrified over this. This is the idea of generics. And without getting too in-depth into this concept, really what you need to know is that it's kind of our way of like templating this node. And so what that means is like, these nodes can hold more than just one type of data. They can hold integers, they can hold strings, etc. So the type that we want this node to hold will take place in this T right here. So if we want a linked list of strings, T will be a string type, and that will take place in the node. But aside from that, we can just think of it as an object where it's storing some data and a pointer to the next node. That's what it looks like in Java, and it's actually quite simple, quite nice. What does this look like in Rust? Well, the very first time that I was putting together this lecture last semester, I went ahead and I had to do some research of my own. And when I wanted to look into this topic, I was greeted with some terrible responses on Google. Why writing a linked list in Rust is so damn hard. Why writing a linked list in Rust is basically impossible. If you were to show me a linked list implementation in Rust and C, I would be wondering why Rust exists. This all was not a very nice sight to see. But after some digging, you'll notice that writing a linked list in Rust actually isn't that bad. You just have to have a good understanding over smart pointers and the ownership and reference concepts that we talked about in the second lecture. So let's get straight into it. Why is it so hard in Rust? Why did people make all of these posts? What's the issue here? So we looked at the Java object representation of the linked list node. What if we did the same exact thing in Rust? What if we use just a struct where we use a generic similar to what we saw in Java? It holds a data and it holds a next pointer to the next node. To this, Rust has a huge problem. It is not this simple. Why? Why is that? Well, a very important thing is that at compile time, Rust needs to know how much space a type will take up. And so, what I mean by space is like, well, with an integer, we know that it'll take 32 bits at compile time. We know that that's not really going to change or anything like that. So at compile time, Rust needs to know how large a type is, and that goes for these structs as well. So this is from the Rust textbook, and this isn't a linked list that we're looking at here. This is actually another data structure known as the cons list. Don't worry too much about the data structure. The data structure is not the focus here. What I want you to focus your attention here is that we have a list type right here and a list type right here. So at compile time, Rust will look at this and they'll say, okay, so a list takes some amount of memory, and the reason why it takes some amount of memory is because inside of the list type, we have another list type which takes some amount of memory. And so the list type is another list type which takes some amount of memory. And we keep on going and going because it never resolves. We have no idea how big a list is because we're using a list inside of the list. So Java, they're fine with that because the way they do things in Java is a bit different from Rust. But Rust, we need to know the size at compile time, and this kind of recursion of types makes this a bit difficult. And so a nice little visual for what's happening there can be seen right here. So, we say that we have this cons list, which takes some amount of memory, and inside of that, we have another list, which takes some amount of memory, and we keep on going infinitely, and Rust says, I don't know how big or small this node might be. So let's go ahead and go into a Kahoot here. Just one question for now. A minute or two to join, and just to check in to make sure we have the concepts that we talked about so far and we're on the same page. Join in with your net ID as usual. If you don't join in with your net ID, we cannot give you attendance. Because how are we going to know who you are? You can't know who you are. We're going to get started pretty soon here. Give it like 20 seconds or so. We'll get started. So, first question. Just keep in mind what we just talked about. Why does Rust have trouble with this? And let me get my thing out of the way. So this isn't the same node we talked about, but very similar issue. Okay, well done. So, well done to the 55 of you. Red is definitely wrong because this whole lecture is going to talk about why linked lists are supported in Rust. There is such thing as type T. We talked about that at the start, where type T is just basically the type that you want the node to hold. So if you're holding a linked list node of strings, T will be string. It doesn't. This is fine. This is not fine, and I'll show you why. So similar to the cons list example that we saw in the slides, it's a very similar thing here. We say that if a Rust at compile time is looking at this node, they'll say, okay, so this node takes some amount of memory, and inside of the node we have another node which takes some amount of memory, and it keeps on going, saying, this takes memory, and it never knows how much the node actually has, how much memory the node actually has. So a very similar thing that we saw with the cons list example. And let's continue. So, what do we do? So if this is the problem in Rust, how would we do this? How would we do a linked list, a singly linked list? So this is a great time to introduce the concept of smart pointers. So before we talk about smart pointers, we should probably talk about what a pointer is, right? We talked about pointers a little bit in the second lecture, but what is a pointer, right? Let's go ahead and review this. So abstractly, we can think about them as just like an arrow to a value that's stored somewhere else. We can think about it as a variable that just stores the location of the value stored somewhere else. And so, in Rust, we can think about it pretty abstractly like this. In other languages like C, C++, it's a little bit less abstract. Like in those languages, you actually store, you have to work directly with the actual memory addresses, and they're actually stored in the variable, and that's what a pointer is in those languages. But here, we don't have to think too much about it. We just know that this variable stores the location, an arrow to a value stored somewhere else, for example, the heap. So if we know what a pointer is, what is a smart pointer? Well, abstractly, again, they are just pointers, but they have additional features and metadata. These additional features are what makes it smart. It's what makes it a smart pointer. So let's talk about our first smart pointer. And this smart pointer is known as the box smart pointer. So a box smart pointer is a pointer, but the reason why it is a smart pointer is because of the additional features that it provides. And so what are these additional features? Well, what the box smart pointer allows us to do is it allows us to store data on the heap rather than the stack. So if you remember the stack and the heap from the second lecture in the homework, we said that the stack and the heap are parts of memory that are available to your code to use at runtime, but they're structured in different ways. So we talked about how the stack is for elements of a fixed size, and the heap is for elements of an unknown size or a size that might change. So let's take a look here. We have 5, and if you remember from the homework and from the lecture, we know that 5 is an element of fixed size, signed integer of 32 bits. So we know that this would normally be held on the stack. But what happens if we use this box smart pointer? Well, if we wrap it in a box, what this will do is store this element on the heap rather than the stack. And so B, what is left on the stack, is B, which is a pointer to the heap data, which is this data right here. So again, what remains on the stack is a pointer to the heap data. We put it on the heap using the box smart pointer. And so the further additional features that the box smart pointer provides is that it implements dereference, deref. And so this isn't extremely important for today. We are talking about smart pointers, but the focus is kind of the application with linked lists. We don't really need to worry about this too much. Just know it's there. And if you're interested in learning more, we have a lot of students that are really interested in learning more Rust. You can take a look at that here. I've linked the textbook, the book, and you can read into it a bit more there. But what's important for this lecture is that it stores data on the heap rather than the stack. So, quick Kahoot question. What is a box? I'm blocking the answer on this one, but I would hope that you don't even need to see it. So is a box a smart pointer, or is it a container with a flat base and sides, typically square or rectangular? Very much asking the hard-hitting questions here. Someone says, aren't both answers correct? Well, no. And to the 6 people that answered it, you're not funny. Anyway, so well done to the 60 of you. Yes, a box is a smart pointer. that puts stack data on the heap. That is precisely what it is. Well done to the 60 of you. Let's move forward. And let me get myself out of the way here. Okay. So why is this important? Why does this help me write a linked list in Rust? Well, let's revisit the issue that we had with the cons list and also the linked list that we saw in the Kahoot question. What was the issue that we had? Well, we talked about how the issue was that at compile time, Rust doesn't know what the size of this is. It just keeps going infinitely. It never reaches the base case, right? Well, the heap, as we said, is just a general term that describes boxes, but in this case is used to store data of an unknown size or a size that might change. So keep this in mind, because what do we do to store an element from the stack onto the heap? Well, if only we had a smart pointer that could do that. Well, we do, right? We just talked about it, the box smart pointer. We talked about how the list is an unknown size or a size that might change. So we want to put this on the heap, and the way that we can do that is by wrapping it in this box smart pointer. And so now, rather than going crazy and recursing infinitely, what we'll have here is just the size of the cons list node. We know exactly what it is because pointers are of fixed size. And we know this because this is true because a pointer doesn't change size depending on what it's pointing to. Like you can point towards the White House and you can point towards a barn and the size of the pointer will stay the same. So as a result of that, we have solved our issue with the size not being able to be resolved. So what remains on the stack is a pointer to the heap data when using the box smart pointer. So to this, Rust says no problem. So with the linked list, we can just simply wrap the node inside of this box smart pointer, and Rust says no problem, except for one minor thing. So we talked about this a little bit in the last lecture, Rust 3, and we said that in Java, objects can have either a value or they can be null. And you can think about this option type in kind of a similar manner, where we say that to tell Rust that our node struct data will either have something or nothing, we need to wrap it in this object type. So what does that look like? Well, we literally just wrap it in this object type, option type, sorry. This option type, basically symbolizing optionality. It can either have something or it can have nothing. So Rust says to this, no problem, and that's for real this time. If you wanted to implement a singly linked list in Rust, this is probably the way that you would do it. And so very doable, very possible. All of those posts are a bit dramatic, but you can see why it's a bit more complicated than what you'll see in other languages. And the reason why that is because of the kind of properties that you see in Rust. It's not always as straightforward. So if we want to talk a little bit more about the implementation here, we can use this node that we've created using our slides and see kind of how we can use it to implement a real linked list. So this is a very, very basic linked list implementation. We can create nodes. So for example, we have two nodes. One is a node that is storing nothing, or sorry, one is that is storing the value 1, and the next pointer is currently pointing to nothing. This is another node here, so you can imagine two nodes in memory just kind of created. One is holding 1, one is holding 2, and if we want to set the pointer from one node to another, we can call this function that we created up here, where we say that the next pointer of the node is going to be the parameter to this function, which is this node right here. And so what we do is we wrap it in sum, basically saying that there is now something here, rather than pointing to nothing. And we wrap the next pointer in a box, so that way we know the size of it at compile time. And that's that. These two nodes will now be connected if we were to do that. So that wasn't too bad, right? That wasn't too bad. What about doubly linked lists? So not sure if you guys have kind of covered doubly linked lists before, but if you know what a singly linked list, it's not too complicated. So doubly linked lists are the same as singly linked lists, except instead of having only a next pointer, they will have a previous pointer as well. What does that look like? Let's take a look here. So normally with a singly linked list, we'll see that this node would point to, it would have a next pointer to this node and so on and so forth. But since it's a doubly linked list, we also have a pointer to the previous node as well. So, what does this look like in Java? It's very similar to what we saw with the singly linked list node. We just add a pointer to the previous node while we're at it. And so to this, again, Java says no problem, no worries. Java handles things a lot differently than Rust, so Java has no problem with this. But is it this simple in Rust? As you might imagine, absolutely not. So, no. Uh, Rust, if we were to do exactly what we did with the singly linked list, if we just wrapped it in a box, wrapped it in an option, and shipped it out and called it a day, Rust would say there is a big problem here. I don't even think it would compile. Why? What's wrong? Why would it yell at us for this? Well, if you remember from the good old second lecture of Rust, we had some rules of ownership. And if you remember these, it says, rule number 1, each value in Rust has a value that's called its owner. Rule number 2, there can only be one owner at a time. This is very important. And rule number 3, when the owner goes out of scope, the value will be dropped. But what's important here is rule number 2. There can only be one owner at a time. So what does that mean? Well, in our doubly linked list, if we have a pointer to the next node and we have a pointer to the previous node, let's take a look at, for example, let's choose this node. This node will be the owner of this node, and this node will also be the owner of this node. So we have a big problem here. This node has two owners, where, we said it can only have one owner at a time. So Rust will throw a fit. How can we accomplish the doubly linked list in Rust? Well, if only we could have multiple owners in Rust. How could we do this? Let's talk about our second smart pointer. So our first smart pointer was the box smart pointer. Now we can talk about the RC smart pointer. So sometimes we actually need to be allowed to have a value that has multiple owners, and a doubly linked list is a great example of this. So RC is short for reference counting. And so this type keeps track of how many references we have to a value and then cleans it up when we're done with it. And so this is a smart pointer because of the additional feature that it provides. It is a pointer with additional features, and that additional feature is reference counting. So how does this smart pointer work? Well, there is a very nice analogy from the textbook that relates it to a TV in a family room. So let's imagine the RC smart pointer as a TV in a family room. And so when one person comes into the living room and starts watching the TV, they'll turn it on, and others can come into the room and watch the same TV. But when the last person leaves the room, they'll turn off the TV because it's no longer being used. If someone turns off the TV while others are still watching it, there would be a huge problem from the other people that are watching the TV. So how does this relate to Rust? Why is this important? Well, let's think about this family room as kind of like, let's think about the TV as a value in Rust. And every person watching the TV is the owner of that TV in Rust, right? So if I come into the living room and I'm watching the TV, I am now the owner of the TV. If someone comes in and watches that TV, they are also the owner of that TV. If we deleted that value in memory, if we deleted the TV while all three of us were watching it, that would mean that we have like three dangling references, three people that are pointing to something that doesn't exist in memory, which if you remember from the second lecture was a big problem. So the RC smart pointer just makes sure that the value isn't deleted until everyone is done with it. The value isn't deleted until everyone is done watching the TV. So that's kind of the intuition behind this reference counter, the RC smart pointer. So from the Rust textbook, I don't want you to get too confused with the crazy syntax that's going on here. Really, the most important part of this slide is how the pointer keeps track of the amount of people that are, owning the value. So let's take a look at this. So we have the count after creating A. And so we'll print out after creating this variable B. We'll print it out after creating this variable C. And what's important is that C is being created within this scope right here. In many languages, you can use these braces, these curly braces, to create your own scope, the same way that, like, for example, the main function is its own scope. So here we have C created in its own scope, and once it hits this brace, just like any other variable, it'll go out of scope, and we'll be printing it throughout. So what is this output? Well, at this print line, it'll say that we have one reference, because it keeps track of the reference counting. After we create B, it'll say, okay, we have two now. after creating C within this scope, it'll say we have 3, but then C will go out of scope, so it'll decrement the reference counter, and on this print line here, it'll say that we only have 2 references to that element in memory. So now you can kind of see how this reference counting works. So with the doubly linked list, let's revisit the node that we created. What if we replaced the box smart pointer with the RC smart pointer? Because we said that the issue before was that we can't have multiple owners. But now RC has some very fancy Rust magic working on, and does it solve this problem? Well, to this, Rust says, no problem, kind of. There's one not so minor thing that we need to talk about. And so that is this rule from the second Rust lecture. At any given time, you can have one mutable reference or any number of immutable references, but not at the same time. This is really important because just like the compile time borrowing rules, so these are the compile time borrowing rules, we talked about how, if we have, for example, here like two immutable references and one mutable reference, Rust won't even let your code compile. And this is one of the beauties of Rust. In other languages, if you're making these kinds of mistakes and you're fumbling around with your variables and your values in memory, C++, it'll let you compile, but once things actually go wrong, it'll be a runtime error, or it'll be some errors that you won't really notice until things are kind of acting fishy. Rust won't let you compile, according to these rules here, right? So let's talk about our third smart pointer, refcell. What refcell lets us have is many immutable borrows or one mutable borrow at any point in time. So in other words, this smart pointer just lets us break a bunch of rules. So what's the difference though? Well, refcell keeps track of how many immutable and mutable borrows that we have. And refcell, the distinction is that it'll panic at runtime if you are caught trying to have more than one mutable borrow instead of not letting you compile. So it is kind of letting you break the rules, but the difference is that it'll let you compile and it'll just kind of scream at you when something goes wrong, versus what we saw with the borrowing rule where if something goes wrong, your code won't compile. So refcell will let you actually have multiple immutable or immutable borrows, but with that distinction that we talked about. So with the doubly linked list, what we can do is just wrap it, in the innermost layer with refcell, and to this, Rust says, no problem. Finally, we have done it. We have implemented the doubly linked list, and you'll notice here we say that we can do better. Why can we do better? Kind of out of the scope for this lecture. If you're interested in why this doubly linked list implementation isn't really ideal, you can read more about it at this link. Same thing as earlier, we have a lot of students that are really interested in learning more about Rust. If you are, that's an excellent read. I think it's really interesting, and you will enjoy it quite a bit. So someone asked in the chat, could a linked list be implemented in a complicated way? Probably, but with borrowing. I think you asked that question earlier, and I hope those slides answered that. If it didn't, let me know. Let's have a Kahoot question. What is RC? Let me get my camera out of the way. So is RC a type of cola that isn't sold anywhere? Is it a regular pointer? Is it a smart pointer that has reference counting? Or is it a smart pointer for putting stack data on the heap? Alright, well done, yep. It is a smart pointer that has reference counting. Well done. Very well done. Okay. So, some final notes here. A little bit of a shorter lecture today. Do we implement data structures in real life? I think this is an important question to answer because a lot of people, once they first start learning the deep implementations of data structures, in this case it's a little bit more complicated because we're writing it in Rust, but even if you're writing it in Java or C++ or C or whatever it is, Python, do we implement them in real life? Well, honestly, for the most part, implementing these data structures are, for the most part, just really good pedagogical tools. So for example, in this lecture, we were able to use linked lists to kind of teach and use it as the driving force for some other concepts. So they're great pedagogical tools. Usually, if you need them in real life, you'll probably just use a library because it's a lot of work to implement your own data structure. But usually, you'll probably just use the library and like edit the library if the data structure doesn't let you do something that you don't want. And many interview problems are just data structures questions. And this is why classes like CS225 are so helpful. In a lot of interviews, you'll find yourself like getting a question where it's like implement this part of some data structure or use this data structure and edit its implementation to have this functionality. And also, you generally don't really want to be using things that you don't understand. So, in general, you don't really implement data structures in real life. However, understanding them very deeply, understanding what's actually going on under the hood, very important, and it allows you to do well in your interviews and actually be able to understand what's going on under the hood. So that's it for today's lecture. A little bit of a shorter lecture, but I hope you guys found it interesting. A lot of people really enjoy this lecture because it's a little bit of a fun one, I think. If you have any questions, feel free to ask away in the chat. Thank you.